Hi everyone, this is Sugantha Priya, Assistant Professor, Department of Computer Science, Dr.S.N.S. Rajlakshmi College of Arts and Science. This presentation is about deadlock avoidance in operating system. When two or more processes try to access a critical session at the same time and they fail to access simultaneously or struck while accessing the critical session, this condition is known as deadlock. Every process needs a few resources to finish running. The procedure makes a resource request. If the resource is available, the OS will grant, otherwise the process will wait. When the process is finished, it is released. Deadlock can be avoided if certain information about the processes are available to the operating system before the allocation of resources. For every resource request, the system sees whether granting the request will cause the system to enter a unsafe state. That means the state could result in deadlock. The system then grants only the request that will lead to a safe state. There are two possible states whether to check whether a deadlock is avoided or not. That is unsafe state and safe state. A state that may allow deadlock, it is possible for a process to be in unsafe state, but for this is not result in the deadlock. Safe state, a safe state, it has a bunch of process and there are enough resources for the first process to be finished, and after it releases its resources, then there are enough resources for the next process to proceed, so there is no chance of deadlock. Next is deadlock avoidance. In order to determine the condition of the next state, whether safe, unsafe or deadlock, the system must know this information in advance. Resources that are currently available, resources currently allocated to each process, resources that will be required and released by this process in the future. To avoid deadlock, we have to follow the simple rule. If the request causes the next state into unsafe state, the deadlock, then we should proceed to the next condition. Next is the resource allocation graph. The resource allocation graph is used to visualize a system's current state as a graph. The graph includes all processes that are assigned to them as well as the resource to that each process request. Sometimes if there are fewer processes, we can quickly spot an algorithm in the system by looking at the graph rather than the table. So we use a Banker's algorithm for the deadlock avoidance. Deadlock avoidance can be done with the Banker's algorithm. A Banker's algorithm is a resource allocation and deadlock avoidance algorithm which tests all the requests made by the process for the resource. It checks for the safe state or an unsafe state. After granting a request, system remains in the same state. It allows a request, and if there is no safe state, it doesn't allow the request made by the process. These are the three inputs to the Banker's algorithm: max needs of the resource by each process, currently allocated resource by each process, maximum free available resources in the system. The request will be granted only under these conditions. If the request made by the process is less than to the max need for that process, if the request is made by the process is less than the equal to the freely available resource in the system. So if you see in these examples, so we have a free space, free resources, total number of allocated resources it is 10. So the total number of free resources it is 3. So when the demonstrate that the particular process is in the safe state. If you see in the next diagram, the process is not in the safe state, which means a deadlock is going to occur. Next is a Banker's algorithm for a single resource. So here in this diagram, so initially all the process A, B and C, D are free. Next is the process is allotted to the resources and the free resources it is 2, whereas in the next diagram the free resources is 1. So there are 3 resource allocation states here. One is safe state, say unsafe state. Next is the Banker's algorithm for a single resource. The scheduling algorithm can avoid deadlocks is known as Banker's algorithm. It is modeled on the way that the bankers might deal with a group of customers. This algorithm is going to check whether the request leads to a safe state or an unsafe state. This is a Banker's algorithm for multiple resources. Here we have multiple resources like tape drive, plotter, scanner and CD-ROM. So we have different processes named from A, B, C, D and E. Next is the resources assigned for the each process. So next is the resources still needed. So E is the existing available resources, that is we have 6 tape drives, 3 plotters, 4 scanners and 2 CD-ROMs. So next is P. So P is the number of resources that is used by the process, that is 5, 3, 2, 2, 1, 2. Next is the available resources. So available resources is equal to 1, 0, 2, 0. So the banker's algorithm deals with handle multiple resources. Next is deadlock prevention, attacking the mutual exclusion condition. In the mutual exclusion condition, some devices like printers can be spooled. Only the printer daemon uses a printer resource. Thus, deadlock for the printer is eliminated now. We cannot spool all type of devices. So, the principle in the deadlock prevention is avoid assigning resource when not absolutely necessary. As few process as possible actually claim the resource. Next is the attacking hold and wait condition. It requires processes to request resource before starting. So the problem is we may not know required resources at the start of the run. So there is a variation in the processes. So the process must give up all the resource, then request all the immediately needed. Next is attacking the no preemption condition. So consider a process given a printer. So it is halfway done its job. Now forcibly take away the printer. Next is attacking the circular wait condition. In the circular wait condition, we have different types of resources like image setter, scanner, plotter, tape drive, CD-ROM, etc. So initially order all resources and allocate a resource graph for all the resources. So next is the attacking the circular wait condition. If the condition is mutual exclusion, the approach is you have to spool everything. If the condition is hold and wait, you have to request all the resources initially. If the condition is no preemption, you have to take the resources away. If the condition is circular wait, you have to order the resources numerically. So this is a summary of approaches to the deadlock prevention. Thank you.